Okay, so yesterday we covered, so let's do capacitance of spherical and cylindrical capacitors. So capacitance of cylindrical and spherical capacitors. So parallel plate would be if the capacitor is two plates like this. This is the one that we covered yesterday, parallel plate. So you could do plus plus, minus minus, right? And then you can trap the electric field between the plates, and you can use that electrical field for your electrical energy. So that would be the basic design of the capacitor. So you could also have a cylindrical capacitor like this, some kind of very thin rod. That could be, let's say, positive. And then you can have a cylindrical shell outside of it. You know, so let's say this is the negative and this is the positive. And the electrical field is flowing outward like this. So the cross section of this would look like this. This is the inside cylinder. The electrical field is going this way. And then you have the outside cylinder. Could be a very thin shell like this. Like that, okay? And then you could also have a spherical. So you could have a ball, and then you could have a spherical shell. And then the electrical field is going like this. This is a cylindrical and spherical. And of course, the region in between them, if it's air, then the kappa will be just one, right? But if you put a dielectric material in there, right, and then you could say, oh, okay, that would increase the capacitance by a certain factor. Same thing here, you can put a dielectric in here also. So let's derive the let's derive the capacitance of this. C is Q over delta V, right? So then you're saying this has charge Q, and then let's say the outside has charge negative Q, but the order doesn't matter. The inside could have negative Q, and the outside could have Q. So then the electrical, what would be the voltage difference between the two plates here? Then it'll be equal to the integral of the electrical field between the capacitors, right? Then the integral would go from the inner radius to the outer radius. So E dot dr RA to RB. Or we can call them R1 to R2. So the inner radius to outer radius. So then the electrical field outside the cylinder is, remember, we derived that 2k lambda over R, integral 2k lambda, the charge density over R dr from R A to RB. And then the integral of that is going to be an ln function. So Q over 2k lambda. 2k lambda is constant, so it comes out of the integral. And then the ln of R, RA to RB. Then you're going to have Q over 2K. And then the charge, the linear charge density is going to be Q divided by the length of the rod. All right, so you're dividing the charge of this rod divided by the L, and then ln of RB to RA. And then the Q's cancel. And that's the capacitance. So it should be L over 2K ln of RB to RA. Okay, so let's see again if it has similar features. So remember, in terms of units, it needs to kind of work out. So if this is farads, right? So remember, what was the units of capacitance? It was farads. And that was what? The definition of capacitance was Q over V. So it was Coulomb per volt. So the farad is just the name for 1 Coulomb per volt. So the capacitance units is 1. Well, this is confusing because capacitance is C. And then 1 Coulomb is the unit for it. 1 Coulomb per volt. So 1 farad is 1 Coulomb per volt. So I'll write this in units. So 1 Coulomb per volt. And then you got here, this is meter squared over meter times units of E0. And of course, the units of E0 are such that it will work out when you would calculate it, that it will all cancel whatever the units of E0 are, and it will give you a Coulomb per volt. So this needs to be kind of the same units in the sense that if this is meters and well, 1 over, if we want, we could write this in terms of E0 to compare it to that. Then we could say, oh, the constant K is 1 over 4 pi E0. So then 1 over 4 pi E0, right? And then it'll be, this will be 2 pi and you'll go to the top. So it'll be 2 pi E0 L over ln of RB to RA. So if we were to write it the same way that the capacitance of a parallel plate is usually written. Let me see. So I'm not sure how I write it in my formula sheet. Let me see. In my so this is the formulas that are kind of relevant for this next chapter. I've got the formula for the voltage difference between 2 points, the voltage of a point charge, potential energy, electric field is negative derivative of potential energy, capacitance is Q over delta V. So I've got the parallel plate AE0, the cylinder, yeah, I wrote it in terms of the E0, right? So it should be 2 pi E0 L ln divided by ln of D over A. Yeah, so D is the outer radius, and then the A is the inner radius. Okay, and then once we derive the sphere, we can write it in terms of the E0 also, and it'll be RA RB over RB minus RA. And then the next thing we're going to derive is the potential energy equation for the potential energy of a capacitor. And then the last topic is the torque topic. torques and dipole moments. Okay. So you can see it's got now the E0 is on top. So then what units should it have? So then it should be meters, right? And then this is meter over meter, so that cancels. So this is unitless. And then so it's meters times E0, the units of E0. So then that should work out because this also had meter times units of the E0. Okay, cool. So in terms of units, it works out. The other thing we can check is in terms of, let's see if it makes sense in terms of just logic. So if the length of it's telling you if the length of the cylinder is big, the capacitance is bigger. So if it's longer, well, that's kind of like saying here, the area, if the area of the parallel plate is bigger, you should be able to store more charge, you see? So yeah, then if the cylinder is bigger, you should also be able to store, of course, that would mean the outer cylinder is also bigger. So then, of course, that makes sense. How about this part? Does that make sense? The radius being closer. Okay, so the closer that this radius is to this, right? The closer they are, their ratio is going to be closer to 1. What's ln of 1? You see? So as RA approaches to RB, then ln of their ratio approaches zero, right? Because as this radius approaches this radius, then their ratio becomes closer to 1, and then ln of 1 is 0. Well, that means this becomes a smaller and smaller number, and then the capacitance becomes larger and larger. Do you see? So does that make sense? Oh yeah, yesterday we spent quite a bit of time on that. We said, if you want to make a capacitor bigger, make the distance smaller, and I gave you this big, long explanation, right? Well, I don't need to give you an explanation again for this reason, because it's the same reason, you see. So it just mathematically looks different, but it's the same reason. So if you want to make this capacitor better, make the distance between the plates very small, you see. So you could also do the same technique that we did yesterday to make a strong capacitor. You could say, okay, put a plate, then a dielectric. Remember that video that we saw? So then you have a metal plate, let's say. Oh, I should use different colors. So then you put a dielectric. And then you put that's already a cylindrical shell right there. You see? And then you make another dielectric. Then you make another cylindrical shell. Which, if you think of it, that's kind of what they did when they rolled this up, right? So they turned it into a cylindrical capacitor, you know. So you basically have a bunch of cylindrical capacitors in series again. So the closer that the plates are to each other, this turns into a very small number and the capacitance becomes a lot larger. Cool. And then how about the sphere? Okay, so then the sphere, we're going to take the same process. Q over integral. So what's the electrical field between the spheres? And it's going to be KQ over R squared, right? So integral E dr, KQ over R squared dr, then the integral of that. So this is the electrical field between two spheres right here. Then you're going to have the KQ comes out. And then integral of 1 over r squared is 1 over r. So then you're going to integrate that from RA to RB, 1 over RA minus 1 over RB. So the integral of that is 1 over r, or negative 1 over r, but I'm taking the absolute value here anyway, so I don't care about the signs. Then I'm going to simplify this. Okay. So then it turns into what? The Q cancels, the Q cancels. And if I write it in terms of E0, this becomes 4 pi E0. And then these two multiply and go to the top, RA, RB over RB minus RA. Okay. So let's do unit analysis and also the meaning analysis, right? That's kind of how I always like to do, is derive something mathematically, then understand it, see if it makes the right units, and see if it makes sense, you know. So then you're going to have meter squared. So you have the units of E0, you've got the meter squared, and then you have meter, basically. So this is units of meter. So then this and this cancels, and there you go. So meter times E0. Okay. So units, they're all the same. Okay. How about in terms of meaning? This one doesn't really have, let's see, the top plays the same role as kind of like this one. Here it's L, but here it's A, the area. So I think this one probably has that idea, is RA times RB. So obviously, if this is a bigger area, right? Let's say it's got a bigger radius, RA, and let's say RB is bigger. You see? So if you compare this capacitor to this has a more capacity to store charge because it's got a bigger surface area of this plate, you see? And of course, this has more, this is a thin spherical shell. So of course, this is going to have more capacity to store charge too, you see? So if you increase both of them, RA and RB, you're increasing the area of both, of course. So this is what this is telling you. If you increase both of their areas, the product of their radius, that means that increases the capacitance. So that's kind of like saying if you increase the area of the parallel plate, you increase the C. So that makes sense. And then this has the same idea as the distance D, right? So actually, this looks closer to D than the ln thing, because this says as this approaches this, as the radii approach each other, this approaches 0, and then this becomes a huge number. So again, make this gap as small as possible, ideally. Make this gap as small as possible. You see? And again, you could put a bunch of them with a dielectric in the middle, you see? So then that's it. So same idea, and it works for all of them. Let's see if that was the equation. Yeah, you see 4 pi E0. A times V is the product of their radii divided by the difference of their radii. Okay, cool. Any questions on that? Cool. Okay, so now the next thing to do is to go over the potential energy equation.